All right, here we go. So we're going to draw ammonia. So you go to your periodic table. Obviously, nitrogen's going to be in the middle. Hydrogens are never going to be in the middle, right? Nitrogen. And nitrogen has 1, 2, 3, 4, 5 valence electrons. And then you have your 3 hydrogens. And again, this is going to be practice of like, well, where do I line them up? Well, line them up on the lone electron or the single electron because you know that they'll probably bond, bond, bond. Hydrogens each have 1, right? So now we're going to share, share, share. So 1 lone pair of electrons, and then 1, 2, 3 sigma or single bonding pairs. And this is ammonia, NH3. Oh my gosh, you want to hear the cheesiest joke? This is actually perfect timing. What did the 3 hydrogens say to the nitrogen? I'm on ya. Oh, it's so good. Oh, it's so bad, but so good, right? Ammonia, like ammonia, because they're attached to it. Ah, science. Okay, it's sad when I crack myself up. Okay, so here's ammonia. Ammonia. Right? Isn't that so good? Oh, you got to tell someone else that joke. We got to share that joke. It's so good. All right, so here's the Lewis structure for NH3, which is ammonia. Okay, so the nature of covalent bonding, again, is to complete octets, right? And then except for hydrogen, which is okay with a duet. So this is just looking at our diatomics, like F2Cl2, Br2I2. They'll all look like this because those are all halogens, and so they all have 7 valence electrons. But we haven't looked at like, we've looked at hydrogen. So this is H2, right? Hydrogen has 1, this hydrogen has 1, they share, they both have 2, and hydrogen is stable that way. We haven't looked at nitrogen or oxygen yet though. So let's try to draw them. So let's do oxygen first. So diatomic oxygen. So oxygen, oxygen. And oxygen's number of valence electrons is 6. 1, 2, 3, wow. 4, 5, 6. The reason I did that is because I know I'm going to bond them over here, so I strategically place them away from where I know I'm going to bond. 1, 2, 3, 4, 5, 6. So you know in chemical bonds you have to bond everything at least one time or there's no point, right? The problem is, so oxygen has 6, right? Sorry, 6 valence electrons, and there's 2 of them. So I have 12 electrons to work with. Okay, so that I don't get to like include anymore. This is it. This is all I have. So any suggestions? Because if you look right now at this oxygen, 1, 2, 3, 4, 5, 6, 7. It has not achieved stability, and neither has the other oxygen. Right now, neither of these are stable. Any suggestions of what I could do to achieve stability? Oh, LaJames is already on top of this and a couple others. Create a double bond, okay? Because you don't get to just throw in extra electrons, what you do is you pair up this single electron with this one. So I'm going to redraw that because it's ugly. 1, 2, 3, 4. 2 lone pairs on each oxygens, and now I've achieved stability. 2, 4, 6, 8. 2, 4, 6, 8. Now make sure you only have 12 electrons. 2, 4, 6, 8, 10, 12. Beautiful. This is diatomic oxygen. It has a double bond. Now I need to teach you this. A double bond is consistent of a sigma bond and what's known as a pi bond. We will get into that later. So 1, 2. We'll talk about this later. Just for right now, memorize it, okay? a sigma and a pi bond are involved in a double bond. All right, so this is O2. How about you guys try to do N2? Oops. So 2 nitrogens, diatomic nitrogen. And now nitrogen has 5 valence electrons. Okay, you have to bond everything at least once, or there's no point of even doing this. Suggestions? I have not achieved stability. I do not have 8 electrons around either nitrogen. What about like this? Oh, getting closer. 2, 4, 6, 7. What are you guys saying? Yes, triple bond. Awesome. Now, I know that when we're first doing this, this is ugly. So I would like you, once you do this, to please redraw it. That looks horrific. A triple bond. And then don't forget to include your extra lone pairs. So this is a triple bond. A triple bond consists of a sigma bond, that's one bond, a pi bond, that's another bond, and another pi bond. Triple bond. Sigma, pi, pi. 1, 2, 3 bonds. Again, I don't need you to understand this yet. I'm kind of jumping ahead. Any questions so far, besides having no idea what sigma and pi mean, except for memorizing? So lone pair, 3 bonding pairs, triple bond. Okay. So again, oxygen and nitrogen, because their electrons alone and one bond wasn't good enough, had to form multiple bonds. So we can form single bonds or double bonds or triple bonds. So again, let's draw. I should have had to do this first. So like carbon dioxide would be done the same way. So let's practice that. I should see. So what I'm saying, so like next class, I would have a slide inserted so I could draw carbon dioxide. So carbon dioxide. So carbon in the middle, right? It's the most versatile element. And carbon has 4 valence electrons. 1, 2, 3, 4. And then oxygen has 6, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now we've got to bond everything at least one time. So bond them up. And again, nothing is stable. So I'm going to like bond here. And this is ugly, bond here, but this is 2 bonds between this carbon and oxygen. So if I were to redraw, it would look like this. Questions? So again, sometimes multiple bonds are necessary in order to achieve stability. Okay. So notice, this is formaldehyde. Now formaldehyde used to be used in preservation of like bodies. They don't use it anymore because it's carcinogenic. It has a pretty, it's not like nasty, but it's a very distinct odor. When I was in college, the cadavers were still being preserved in formaldehyde. And look at, this is its structure. So look, we've got a double bond here. This is definitely organic, right? Carbons with hydrogens and oxygens.
You're not screen sharing.
Oh, it's, whenever I go to the whiteboard, it doesn't flip back over to my PowerPoint, sorry. So look, you've got the carbons with the hydrogens, right? The hydrogens only bond once, so you'll never see them in the middle of a structure. And then the carbon double bonded to the oxygens, right? So this is a sigma and a pi bond, 1, 2 bonds. Okay. Now look at ethyne. Now remember, if you remember how to name, "-ine" means triple bond and "-eth" means 2 carbons. So there's 2 carbons, there's a triple bond, and then each of the hydrogens are attached to each carbon, right? You don't ever see them in the middle because you wouldn't be able to complete the structure. So this is the structure for C2H2, ethyne. Again, another organic molecule. And then again, a triple bond has a sigma, and then this is a pi bond, and then this is a pi bond. 1, 2, 3 bonds, triple bonds, sigma, pi, pi. And again, we'll talk more about this later. Okay, what about ions? So NH4 plus. Well, plus means I'm going to lose an electron. So the first thing you do is you go, okay, well, nitrogen has 5 electrons, plus hydrogen has 1, and there's 4 of them. So that would be, if it was neutral, 9. But plus 1 means I'm going to get rid of 1 electron. So really, I only have 8. So what do? Well, let's line them up, right? So nitrogen, 4 hydrogens. So I'll just line them up all around the nitrogen. Nitrogen has 5 normally. Okay. And each hydrogen has 1. So I'm going to bond, 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 and then you see this like little loner right here, and I get to take away 1. So you're going to take away from the central atom that 1 electron, which will help you, right? Because now you have an octet of electrons around nitrogen, and all of the hydrogens have 2, which is what we want. So removing that 1 electron actually causes this to be stable. Now, for polyatomic ions, you must put a bracket around them, and outside of the bracket, you must put the charge. So that's the correct way to draw it, with charge. Any questions so far? So this is a Lewis structure for an ion, specifically a polyatomic ion. So let's go back to screen sharing. Okay, now we said that everything in general likes to have an octet of electrons around it. So 2 exceptions to our octet rule, which we call an incomplete octet, are beryllium and boron. So if you look on your periodic table, these elements are here and here, okay? They're pretty small elements. Beryllium has 2 valence electrons. Boron has 3 valence electrons. And they're actually okay. Beryllium is okay bonding just twice with its 2 valence electrons. And boron is okay bonding just 3 times with its 3 valence electrons. So you'll see, if beryllium only bonds 2 times, it only has 2 4 electrons around it, and it's actually okay that way. It can be stable that way. That doesn't mean it can't have 8 around it. It just is okay being stable with just 4. So they call this an incomplete octet, incomplete meaning less than 8. And then again, if boron takes its 3 valence electrons and only bonds 3 times, 2, 4, 6, it doesn't have an octet of electrons around it. It has an incomplete octet, and it is still actually stable that way. So these are exceptions to our octet rule of elements being stable with less than 8. Okay, there's 2 other elements we know that are stable that way, and in fact can't even have 8. Who are they? Hydrogen, right? Who else? Hydrogen maxes out at 2 electrons. Who else maxes out at 2 electrons? Helium, right? All right, any questions on this? All right. So let's just practice drawing them. Let's draw BH3 and BeCl2. So BH3, so boron. 1, 2, 3. Now, boron has 1, 2, 3 valence electrons, and hydrogen has 1, right? Hydrogen, hydrogen, hydrogen. And so bond, bond, bond. So 2, 4, 6. This is the structure for BH3. So it's an exception to the octet rule. It is totally stable this way. Now, again, that doesn't mean it can't have 8 electrons around it. The boron can have 8. It can hold up to 8 electrons. Hydrogen and helium cannot. But boron can, because it's on that second energy level. And remember, there's p orbitals in there. But it is okay this way. It can be stable this way. So then let's look at BeCl2. So Be, beryllium, has 1, 2 valence electrons. So chlorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So then you'll see a bond here and a bond here. And it's okay this way. 2, 4. It doesn't have 8 electrons around it. Now the chlorine does. The chlorine is stable with 8, but the beryllium is not, and it's okay that way. It's an exception to the octet rule. Okay, so just like you can have incomplete octets, you can also have expanded octets. That means atoms that have more than 8 electrons around them. And you go, well, how is that even possible? Well, let's talk about how that's possible. So, for example, sulfur has 6 valence electrons, okay? So it has the potential, it could bond all 6 times. And if it did, it would have 2, 4, 6, 8, 10, 12 electrons around it. And it is totally fine that way. Now, it doesn't mean it will always do this. It just can do this if necessary. And then like phosphorus, for example, has 1, 2, 3, 4, 5 valence electrons. It can bond all 5 times, which would create 2, 4, 6, 8, 10 electrons around it. And it can be stable that way. Now that doesn't mean this is what it will always do. It just can do it. So let's talk about why. Please do the electron configuration for sulfur. Hold on. For sulfur, selenium, and phosphorus, and arsenic. And you can do noble gas notation. So do noble gas notation for phosphorus and sulfur, and then again for arsenic and selenium. I'll give you a second for that. Okay, so this should be what you get for noble gas notations for phosphorus, sulfur, arsenic, and selenium. So I'm just kind of showing you something. So we said phosphorus can do it, sulfur can do it. Pretty much anybody from the 3rd period on can do this. Now that means 1st period elements cannot do this, and neither can 2nd period elements. And we're going to talk about why. So I'm going to throw my electrons in. We'll just do it for phosphorus. Okay, so if you fill this shell right here, you have 8 electrons. However, you have the potential to have more than 8. And so the question is why? Well, the answer is once you get to the 3rd energy level, as you're filling in these d orbitals that are also on the 3rd energy level are empty. And if they're empty, you can throw extra electrons on there. So that's what causes these elements to be able to be expanded. So right, the same with sulfur. Anybody from the 3rd period on has the potential to do this because of empty d orbitals. And then you go, well, what about, so phosphorus, right? its family member is arsenic, it's one below it, you go, well, but the 3D orbitals aren't empty in arsenic now, right? They're full. Well, that doesn't matter because the 3D is no longer your valence shell for arsenic. Your valence shell is the 4th energy level, right? So for arsenic, the 4D orbitals are what's empty because the 4th is your valence shell. So everybody from phosphorus on the periodic table has the potential to have expanded octets. Now remember, I'll switch this. We're focusing on non-metals, right? Because these Lewis structures are for these guys. So while everybody from the 3rd period down can do this, right, we're drawing Lewis structures for covalent compounds. So let me delete this. So pretty much what I'm saying is the 3rd period on, and again, we're talking about covalent compounds. So we're talking about, 3rd period, like everybody on down here that are forming covalent compounds have the potential to do this. And that is because of the empty d orbitals. So that your 2nd period can't do that. There's no such thing as 2D. So you can't have empty d orbitals. So anybody in the 2nd or 1st period is not allowed to do this. Does what say 6s? Which one? Was it on my whiteboard? All right, any questions? Next to the 4p, where? So this is 4s, 3d, 4p. Oh, that's a 5. Sorry, that's a 5s. Because after 4p is 5s. Sorry, it was kind of a little messy. So 5s right here. Okay, so let's get back to the notes. So let's practice. Let's draw PBr5 and SCl6. So phosphorus has 5 valence electrons, 1, 2, 3, 4, 5, and then bromine, 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 right? Now we have 5 bromines, so I have to split up this pair, which we haven't done yet. You just have to. There's no other way around it. And then again, bromine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, bond. 1, 2, 3, 4, 5, 6, 7, bond. 1, 2, 3, 4, 5, 6, 7, bond. 1, 2, 3, 4, 5, 6, 7. Whew. 1, 2, 3, 4, 5, 6, 7. Boom. PBr5. Phosphorus now has 10 electrons around it. It has an expanded octet, and it is okay like that. Okay, so let's draw SCl6. Sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. And now I gotta throw 6 chlorines around it. So 1, and I'm definitely forced to break up all of the lone pairs. And chlorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, bond. 1, 2, 3, 4, 5, 6, 7, bond. So again, I'm ripping apart lone pairs. Sorry about this chlorine down here. Okay, and now sulfur has 12 electrons around it. That is definitely an expanded octet, but it is on your third energy level, so it is allowed to do that. Any questions? Oh, yep, I can go back. PBr5. So someone asked again about the PBr5. So I'm going to do it right here. I am going to show you a shortcut for lone pairs in a minute, but I want to teach you the right way first. So PBr5 is bonded 5 times with its 5 valence electrons. Bromine, bromine, bromine. Okay, so this is what PBr5 would look like. All 5 of phosphorus's valence electrons are being used in a chemical bond. Questions? Okay, so having said that, I'm going to redraw this. Lone pairs, so I highly suggest you don't start doing this until you get very good at drawing Lewis structures. Lone pairs can be represented by a line. So here's what I mean. PBr5, BR. So once you get good at this, you'll probably be able to tell how many lone pairs everything has. So like each bromine has 3, right? So instead of drawing 6 dots around it, this is a lone pair, lone pair, lone pair. 1, 2, 3 lone pairs. 1, 2, 3 lone pairs. 1, 2, 3 lone pairs. And so you'll sometimes see lone pairs done this way. So again, the line represents the lone pair of electrons. This is like a shortcut method instead of having to draw every single one of those dots around the atom. Any other questions about the PBr5 or either of these, I guess? Either of these molecules? Okay, so let's keep going. Okay, so it says explain. For sulfur, you can have SF2, SF4, and SF6, whereas oxygen, only OF2 can exist. So why can't you, right, sulfur and oxygen are in the same family, which means they have the same number of valence electrons. So why can't OF4 and OF6 exist, is what they're asking. So do you know? Well, oxygen is on the 2nd energy level. Sulfur is on the 3rd energy level. The 3rd energy level has empty d orbitals, which allows molecules to have expanded octets. Oxygen cannot have an expanded octet. So if you try to put 4 or 6 fluorines on it, that would require an expanded octet, and there are not empty d orbitals to put the electrons into. So the oxygen cannot do this. Nobody on the 2nd period can have expanded octets because there are not empty orbitals to throw the extra electrons into beyond 8 electrons. Okay, so formal charge is all about adding and subtracting. I am not going to read this to you. This is how it works. We're just going to practice. Okay? So I want you to try to draw thiocyanate. Thiocyanate is SCN minus, okay? And it goes in this order. So then draw the S, draw the C, and draw the N. So S, a C, and an N. So Give you a moment. I want you to try drawing it. Okay, so now you can bond everything one time at least. And at this point, there's a wide variety of options of what you can do. So there are often times where we will have Lewis structures that have more than one possibility of how you draw it. Okay. So what's one way we can do this? Well, let's see. What if we bond there? And we bond here. And then remember, -1 means I get to add 1. So I'll add, and I'm just going to make it blue and a little star. This is the extra electron I get to add. This is one way to do it. So I'm going to redraw S, C, N. Okay. Okay. Now, I think this for right now, oh, okay, in brackets, right? And then the minus. I think for now, based on how much we've learned so far in here, this would be the most logical way to do it. It's probably the way you'd be the most comfortable, just pairing everything up and then adding the electron. The thing is that there are other ways to draw it. So what I need you to remember is that the electrons involved in a compound or in an ion don't belong to each element individually. They are available for every element involved in the compound to be used or do whatever it takes to be stable. Meaning, yes, for right now, we've been drawing the 4 valence electrons to carbon because carbon has 4. However, they don't belong to carbon. They belong to everybody involved in the compound or ion, and therefore they don't have to be stuck on carbon. So what does that mean? Well, let's erase this guy. So sulfur has 6, carbon has 4, nitrogen has 5, and then +1, right? These are my valence electrons. So that's what? 16 electrons that I get to work with. So we could do this. I'll do it again. So carbon, sulfur, nitrogen, and I'll originally assign them like I just did. So okay, carbon has 4, it can contribute. Sulfur has 6. Nitrogen has 5. Okay, and now we bond everything one time at least. Well, there's actually a bunch of other things you can do. Meaning, like, watch this. I could take this electron right here and I can give it to sulfur. That would complete sulfur's octet. Okay? And then what can I do? Well, I haven't included my extra electron yet, right? So I need to do that. My 1 extra electron because it's a -1. So I'm going to give that 1 extra electron back to carbon. And then I'm going to bond. So it would look like this. So this is another possible Lewis structure. Oops, I forgot my brackets. Okay, this is what I'm saying is those electrons don't like belong to the element. They are there and available, but they're available for any element and whoever needs it. So again, this is showing that this is an alternate Lewis structure. We had this one and we had this one. So on the next slide, what I have is 3 different ways to draw this. Okay, now formal charge is done like this. Formal charge is done, I'm going to cross this off, where you assign numbers to the element based on how many valence electrons it generally has and how many have actually been given to it in the Lewis structure. So here's how we do this. How many valence electrons does nitrogen have on the periodic table? It has 5. How many does carbon have? It has 4. How many does sulfur have? It has 6. Nitrogen has 5. Carbon has 4. Sulfur has 6. So again, you give it how many valence electrons it has according to our periodic table. And then you subtract how many have actually been given to it in the compound or in the Lewis structure. So look at, if you count the electrons for nitrogen, 1, 2, 3, 4, 5, 6, 7. It has been assigned, and you only include one of the electrons in the bond, okay? It has been assigned 7 electrons. So you subtract that from how many it normally has. So what's 5 minus 7? Well, -2. So the formal charge on nitrogen is -2. So what about carbon? Carbon has 4 according to the periodic table, and I have assigned, remember, it's only 1 electron for each bond. 1, 2, 3, 4. So 4 minus 4 is 0. So no formal charge on carbon. Okay, sulfur is, according to the periodic table, 6. So let's count. How many have I assigned to it? 1, 2 for the lone pair, 3, 4, 5. So 6 minus 5 is +1, right? So the form, it's 1, but we're doing charges, right? So it's +1 on the sulfur. Now, all of the formal charge better add up to the charge of the ion. So if it's -1, it better add up to -1. If it doesn't have charge, it better add up to 0. If it has positive charge, it better add up to positive, whatever. So what's -2 plus 1 and plus 0? -1. Okay, so this matches. So this is formal charge on this structure. So now we need to do it again for this guy. Nitrogen has 1, 2, 3, 4, 5, 6 electrons assigned to it. Carbon has 1, 2, 3, 4. Sulfur has 1, 2, 3, 4, 5, 6. Okay, so what's 5 minus 6? -1. What's 4 minus 4? 0. What's 6 minus 6? 0. 0 and 0 and -1 add up to -1. Let's do it again. Nitrogen, 1, 2, 3, 4, 5. So that's 0. Carbon, 1, 2, 3, 4. So that's 0. Sulfur, 1, 2, 3, 4, 5, 6, 7. So that's -1. 0 plus 0 plus -1 is a total of -1. Okay? So now you go, well, which one's the best? So the compound, the molecule, the ion, whatever you're drawing, that has the lowest formal charge is the best. So do you see this has 2's and 1's in it? And this one only has a bunch of 0's and 1, 0's and 1, meaning these two have the lowest formal charge. 2's and 1's are like higher formal charges. So this is not the best structure. It's a possible structure, but it's not the best structure. So now you go, well, how do I pick? Right? So if this is 0, 0, -1, and this is 0, 0, -1, well, their formal charges are very similar. In fact, they're identical. But there is a way to pick. Does anybody want to guess what it is? Look at who gets the negative charge. In the second ion, the nitrogen got the -1 charge. And in the third ion, the sulfur was assigned the -1 charge. Who do you suppose should get the negative charge? The one that is more electronegative, because that would be the one that would attract the electrons more to make it negative. So who is that? Nitrogen is more electronegative than sulfur. This is the best structure. It has the lowest formal charge, and the more electronegative has been assigned the negative charge. Right? So we're sharing electrons, and nitrogen's going to be like, but I'm not going to share that well. So it will be more attracted to the electrons than the sulfur. So it should be the one that has the negative charge. Now, this doesn't mean it's not possible. It's just not as good as this one. Yeah, nitrogen's more electronegative than sulfur. Remember, the three most electronegative elements are fluorine number 1, oxygen number 2, nitrogen number 3. Those are the top electronegative elements that exist. Okay. So, let's talk about bond dissociation energy. So, bond dissociation energy is the amount of energy required to break a covalent bond. And the energy is released in the formation of a new bond. So breaking bonds, remember this is actually ties into thermo. Breaking bonds, endothermic. Forming bond formation is exothermic. Okay, so in order, the numbers are equal and opposite in sign. So what does this mean? This means that, okay, to break HCl apart, you have to put in 432 kilojoules probably per mole of energy, right? You take HCl and you rip it apart. Well, that means if HCl is formed, that same amount of energy is released. Breaking bonds is endothermic, and forming bonds is exothermic. And now notice they're the same exact number, but just opposite in sign, because remember the signs tell you energy going in, energy exiting, leaving, given off, released, however you want to look at for exothermic. So you know that nitrogen's more electronegative because I told you that a long time ago. You just need to memorize it. Oxygen, or fluorine, oxygen, nitrogen. And the reason that nitrogen's more electronegative than, let's say, sulfur is because it's smaller. So it has the ability to attract electrons better than sulfur will. Electrons can get closer and be more attracted to the nucleus because it's smaller in size than sulfur. Nitrogen's on the second energy level and sulfur's on the third. Okay, so single bonds have 2 electrons involved in them. They are the easiest to break and they're the longest. Okay, so if I were to draw like relative in size, you would go like this. Now I'm not gonna, this is gonna be just general, okay? So like single bond, double bond, triple bond. Easiest to break, longest distance, harder to break, a little bit shorter, even harder to break, and shortest distance. Okay, so long bond length, short bond length. Think about it like karate chopping to break it apart. Karate chopping through 1 piece of wood is easier than karate chopping through 3 pieces of wood. Okay, triple bonds are the shortest type of bonds and they are the hardest to break, whereas single bonds are the longest and they're the easiest to break. Okay, so again, double bonds, short, hard to break, harder than single bonds. Okay, triple bonds, shortest, easier to break. It's just repeating itself, really. Okay, now what happens if you're comparing everything that had, oh, this isn't happening yet. So look at fluorine single bond. This is how much energy is stored in the bond, which means this is how much energy you would have to put in to break it. Okay, and this is the distance in nanometers, like how far away they are from each other. So this is the longest distance of the 3. O2 we drew earlier, it has a double bond. This is how much energy is stored in the bond, meaning you'd have to put in this much energy to break the double bond. higher energy, takes more energy to break, and they're closer together, which is part of the reason that they take more energy to break. There's a stronger force of attraction if those electrons are closer to the nuclei of the atoms, or of the atoms. So N2, triple bond. Triple bond. Look how much energy. Look at how much energy is stored in a triple bond, 941 kilojoules per mole. That's a lot of energy you would have to put in to break through the triple bond. And then look at, it's the closest together. The two nitrogens are the closest together. So like N2 and then O2 further apart, and then F, again, I'm just trying to do relative, okay? Easy to break, hard to break. And then this is kind of like middle of the road. Okay. So now we need to talk about bond order. It's actually a little bit more complicated than this, but for the sake of this class, we'll count how many bonds there are, double, single, triple. So a single bond counts as 1, a double bond counts as 2, a triple bond counts as 3. So like N2, if you draw it, it looks like this. This has a bond order of 3 because it has a triple bond. O2 has a bond order of 2 because it has a double bond. Cl2 has a bond order of 1 because it has a single bond. And then you go, oh, nitrate, what? 1.33. So now I have to introduce you to this new concept called resonance. So please draw nitrate. Now nitrate is a polyatomic ion. So nitrogen has 5 valence electrons, oxygen has 6, and there's 3 of them, right? And plus 1 more because of the -1. So I have 24 electrons I get to work with. So I want you to take a moment. I'm actually going to pause this. I want you to try to draw this without me. All right, I haven't bonded anything yet, and I also haven't, so I've included these electrons and these electrons. I have not added my extra electron. Generally, what I do is I bond everything at least one time, and then I kind of look and see where that extra electron is needed, okay? Oh, I don't like this. Okay, so this is that bond right here, okay? So now I go, okay, what can I do? Well, I don't know. I need to add an extra electron. Pretty much nothing is stable at this point. So I'm going to add an electron to one of my oxygens, either this one or this one or this one, because adding it will cause either one of them, whichever one I pick, to be stable. It will have 8 around it. It does not matter who you pick. Now I'm going to put it red so you know that this is me adding the extra electron. Okay, now I have just had this oxygen achieve an octet and nothing else is stable. Suggestions via speaking and not in the chat. Like pretty much you're going to be forced to break up the lone pair because this oxygen is not stable and neither is this oxygen. Any suggestions? Do these electrons belong to the nitrogen, or are they able to be used by any other element in this ion? The answer is yes. So what I'm going to do is because these oxygens aren't stable, I'm going to mess with it. I'm going to take this electron right here, and I'll put it as orange so we know that it came from the nitrogen, and I'm going to let this oxygen have it. And breaking up the lone pair. That leaves me with 1 electron up here, right? Suggestions. Okay, so what if I do this? Is this stable? If I give that extra electron to this oxygen, is this stable? Yes or no?
Yes.
How many electrons are around nitrogen right now?
3.
2, 4, 6. Is 6 stable for nitrogen? No. What does nitrogen need to have to be stable? 8. Okay, so you don't get to do that. I'm putting that electron back. Any other suggestions?
A double bond.
Great. What about a double bond? So I'm just going to move it down so it's not as ugly. So this electron, I'm just going to put it down here so that you can see where it's going to pair up, right? What about a double bond right here? So 2, 4, 6, 8 electrons around nitrogen. That's good. Well, let's look at all the oxygens and make sure they have 8, right? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Beautiful. Everything has 8. Questions? Okay, I want to show you one more thing. Why can't I do this? I'm going to tell you right now, this is wrong. Why can't I split up this lone pair right here and create like, right, I'm going to put this electron, I'm going to just relocate these 2 electrons just so you can see. So I'm going to put one just down here so I can line it up better. And then I'm going to put the other one right here so I can line it up better. Why can't I do this? Why can't I do 2 double bonds? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10. Why can't I do that? Yep, there's nitrogen is not a period 3 element. You are not, this right here, it does not get to have an expanded octet. Phosphorus, sure, but not nitrogen. You cannot do that with any element that's not in period 3 or below. So this is not allowed. So let's go back to my beautiful drawing that looked like this, and then we had a double bond here, right? And then we moved that other, so we created with that lone pair, we broke it up. We put one of the electrons over here to complete the octet for this oxygen, and then we shared and created a double bond with this oxygen. Okay, we need brackets, yes. -1. All right, so now what? Well, I'm going to redraw this so it's not as ugly, okay? Okay, this is nitrate. So when we do bond order, because we have different types of bonds, we have 2 single bonds, and then we also have a double bond. We don't have just a normal bond order. So what you do for bond order now, when there's different types of bonds, is you count how many bonds there are. There are 1, 2, 3, 4 bonds. And then you divide it by how many things are attached to the central atom. There are 1, 2, 3 elements attached to the central atom. So the bond order is 1.33. Well, what does that mean? Bond order of 1 is single bond. Bond order of 2 is a double bond. So 1.33 kind of falls right here. What this means is in real life, you don't have like a short bond and then 2 longer bonds. In real life, all of these bonds are the same exact length, and this is defined as resonance. Because I arbitrarily decided to put my extra electron right here. Couldn't you have put it here or here instead? And the answer is yes, and all that it would have done is just rotated where the double bond would have been. Meaning, there are 3 different ways I could have drawn this, neither of which is better than the other. So I could have drawn it like I did the first time. Okay, that's one way, -1. Okay, and then I also, this is just an arrow saying I could have also put the double bond over here. There's no reason that I couldn't have. This is another way I could have drawn it. Or I could have put the double bond to the left. Neither one of these is better than the other. They're all the same, just with the double bond shifting to different nitrogen-oxygen bonds. Down to the bottom, over to the right, over to the left. 3 different resonance structures. So now again, what I'm saying though is that, like, right, we said double bonds are shorter than single bonds. So there isn't like a short bond and 2 long bonds. That's not really how it is in real life when they've looked at it. What they've noticed, I'm going to clear this now, is that extra bond, that double bond, those extra electrons in the multiple bond are shared evenly throughout the ion, meaning all of these bond lengths are 1.33, 1.33, 1.33. They aren't 2, bond order of 2, 1, 1. This is not true. Now we draw it like this to represent it, but truly all of the distance between the nitrogen and oxygen atoms are all identical. And that's called a bond order of 1.33. So when you look at it, even though there's 3 different ways you could draw it, truly those electrons in the double bond are evenly split up throughout the ion. So all of the bonds are identical in length. So that's what it means to have resonance. And you will see resonance oftentimes in molecules or ions that have multiple bonds. Now, that doesn't mean anything that has multiple bonds has resonance, but that's where you find them. In molecules or ions that have double or triple bonds can sometimes also have resonance. So look at ozone. If you were to draw ozone, it could look like this. Oops, am I not? Okay, so again, those electrons in the double bond are evenly split between the nitrogen and oxygen. So this bond and this bond and this bond are all identical in length. So look at ozone. This is ozone, okay? Just because I drew it like this with the double bond here does not mean I could not have drawn it like this. Ooh, that's kind of ugly. So this is one way, but you could just as easily put the double bond on the other, on the other one. Okay, resonance. Now, so what they do is when they look at ozone, so how do I do bond order? You count the number of bonds. 1, 2, 3. 3 bonds. The double bond and the single bond. How many things are bonded to the central atom? 1, 2. So the bond order is 1.5, meaning in the ozone molecule, those electrons in that double bond are evenly split, okay? So this isn't a bond order of 2 and a bond order of 1. This is not how it is. This is 1.5 and this is 1.5. So somewhere, actually smack dab in between a single and a double bond. So when they've looked at ozone and actually measured the length, and this is in angstroms, you'll see that the length between, can't see that. The length between this oxygen and then this oxygen and this oxygen is identical. Okay, this end isn't like short because it's a double bond with this end being long because it's a single bond. Those extra electrons in the multiple bond are evenly split throughout the entire molecule. That's what it means to have resonance. Okay, so again, just because we draw it that way in a Lewis structure doesn't mean that it's truly the only way. So look at ozone, ozone. 2 different ways to draw it, but truly this shows uniform splitting of the electrons symmetrically across the molecule. There isn't like a short end of the molecule and a long end. So this is what it means to have resonance. The extra 2 electrons in this double bond are evenly split throughout the entire molecule, or shared, I guess I should say. And that's what resonance is. So when you have a bond order, right, of 1, that's a long bond, single bond, right? 1 single bond. This is the largest bond. And then you have a bond order of 2, that's like a double bond, right? It's shorter. So if you end up with like a bond order of 1.33, it's shorter than a single bond, but not as short as a double bond, because 2 double bonds are, a double bond is shorter than a single bond, and this like falls somewhere in between. I'm going to skip this for right now. We're going to start class with it the next time. I do want to end on sulfite. So, oh, no, never mind. I'm going to stop here. I just realized the bell's going to ring in 1 minute.